All right, so we're going to talk about a new concept today called electric flux. And flux can be a little bit of a tricky concept, so I'll introduce it a little bit by way of analogy, which is you might have thought about kind of how water or air flows through something. And that's kind of the idea behind flux, is we want to think about flow. And in the context of something like water or air, there's actually something flowing. I could measure how much water is passing through this pipe each second, which would depend on how fast the water is flowing and how dense the water is and how wide the pipe is. For electric field, we already know from what we've done all term that electric field doesn't actually flow. It doesn't go anywhere. But this concept of flux is still relevant because the electric field is a vector. And so it is going to kind of point through various surfaces that might exist in the world. And the way that we're going to think about flux is kind of symbolically as a new concept, a new quantity, which we'll use the capital Greek letter phi for. We'll often call it phi sub e, because when we get to magnetic fields in a few weeks, we'll also have magnetic flux. So the way electric flux works is you can take a surface, like my trusty note card here, and put it in an electric field, maybe an electric field that points to the right and is uniform everywhere. And then you can multiply that electric field and that area vector together. Now, one thing you'll note is that the electric field and the area vector are both vectors, which means we're going to need one of our tools for multiplying vectors together. Electric flux happens to be a scalar quantity. It's a single number that describes how much electric field is pointing through your surface. So I want to take two vectors and multiply them together to get a scalar. We know from physics 211 and 212 that the choice of multiplication we want here is the dot product. So I'm going to take the dot product between the electric field and the area vector. To do a really quick example, if I have an electric field that points like that, and I have a surface that is oriented like so, if I take the dot product between this electric field and that area vector, they're going to point in the same direction, and I'll get basically just the electric field times the area vector. I've got an example for you to do in the get ready questions. So head back over to Top Hat and then come back to the next video and you will see an example where things get a little tricky.